Hello there. In this video we're going to continue our discussion on the golden ratio. So recall what the golden ratio was. Suppose you have a line segment and you were to cut it into two unequally sized pieces. Let's call this first larger piece x and this second piece y. So here y is less than x. So if the ratio of the sum with respect to the largest is equal to the ratio of the largest with respect to the smallest, then this is what we call the golden ratio. And we showed that this value, phi, has the exact value 1 plus the square root of 5 over 2. In this video, we're going to develop a lot of algebraic properties associated with this, and also how one can apply these to some geometric intuitions aside from this line. Alright, so the first property that I'm going to be looking at is the value of phi squared. So if we just use the definition of phi here, if we just take this as the definition now, that's just going to be the 1 plus the square root of 5 divided by 2, the quantity squared, which once we distribute, that's just going to be 1 plus 2 root 5 plus 5, all divided by 4. So this is just going to be equal to, once we combine like terms and divide by 2, that's just going to be 3 plus the square root of 5 divided by 2, and I can decompose that if I want to. I can rewrite that as 2 over 2 plus 1 over 2 times 1 plus the square root of 5. So this value should look fairly familiar. That's just the golden ratio. So therefore, we have our first property. Phi squared is equal to 1 plus itself, which is fairly interesting because the square of a rational is equal to just that rational number plus a single unit, which is interesting. Now, from this relationship, you can actually rearrange this to show that phi squared minus phi minus 1 is equal to 0, right? Which should look familiar because it's pretty much a quadratic equation, right? So therefore, phi is a solution to x squared minus x minus 1 is equal to 0, right? Because if we were to solve this equation, we're going to get x is equal to 1 plus or minus the square root of 5 over 2. So we have one positive solution, one negative solution. So the positive solution to this is actually the golden ratio, right? So what about the other solution, 1 minus 5, the square root of 2? So x1, 1 plus the square root of 5 over 2, and x2, 1 minus the square root of 5 over 2, right? So this is phi, right? So is there anything special about this? Well, we'll get to that later. Alright, so let's look at another example of phi. Let's do the reciprocal of it. So, by definition, this is just going to be 2 divided by 1 plus the square root of 5. Let's see. Well, what can we do? We can multiply top and bottom by the conjugate. That usually does the trick for square roots. So that's just going to be 2 minus 2 square roots of 5 all over 1 minus 5. So that's just going to be 2 minus 2 root 5 all over negative 4. So I'm just going to divide top and bottom by 2. So that's going to be 1 minus square root of 5 all over 2. I'm going to pull out a negative there, right? So, what is this? So there is our other solution. So this number, including the negative, is what some people refer to as the silver ratio, right? So we have the negative ratio and the golden ratio. Now, why do we want the negative of that solution to that quadratic equation? Well, remember, square root of 5 is slightly bigger than 2, so 1 minus that number is going to be negative. So negating that actually gives us a positive number. So the silver ratio and the golden ratio are both positive numbers. And of course, some people, since this is the reciprocal of phi, will denote it as phi to the negative first. And you may even see some people denote it with another Greek letter or whatever. But I'm not going to go through those details here. Right? So of course, from this property, we have a couple corollaries. So x squared minus x minus 1 is equal to 0. Phi, obviously, is the solution, one of them, right? Negative 1 plus or minus the square root, positive 1, sorry. So 1 plus or minus the square root of 5 all over 2. So we have two solutions. We have x is equal to phi, and x2 is going to be equal to negative 1 over phi, right? Now, why is it negative 1 over phi? Because 1 over phi is negative 1 minus the square root of 5 over 2. 1 minus the square root of 5 over 2 is that second solution, and we want the minus of that, right? So it's very easy to see that this quadratic equation can be factored into x minus phi times x plus 1 over phi is equal to 0, right? So that gives us a very special factorization of this particular quadratic equation. Alright, so up to this point, we've proven that phi squared is equal to 1 plus phi, which of course gives birth to this quadratic equation that has these couple of properties. Now what I'm going to look at is 1 over phi. I'm going to look at another special relationship of this particular thing. So where I showed that 1 over phi is negative 1 minus the square root of 5 over 2, which we can of course write as negative 1 plus the square root of 5 over 2. So negative 1 we can write as 1 minus 2 over 2 if we want, right? That's no big deal. And then decompose this fraction into two pieces, namely 1 plus the square root of 5 over 2 minus 2 over 2. So of course that's the golden ratio, minus 1. Right? So we've proven another interesting property. 1 over phi is equal to phi minus 1. Right? Which is interesting, I guess. But not really, because if I multiply both sides of this equation by phi, I'm going to get 1 is equal to phi squared minus phi. Right? Which is pretty much that thing rearranged. Also, as a direct corollary to that, you can find that phi is equal to 1 over phi plus 1, which is interesting. So there's a relationship with the value and its reciprocal. Almost a very beautiful relationship, I think. Alright, so if 1 over phi is equal to phi minus 1, what I'm going to do is I'm going to multiply both sides of this equation by 1 over phi. So I'm going to get 1 over phi squared is equal to 1 over phi times phi minus 1. So that means what? So 1 over phi squared is equal to 1 minus 1 over phi. And this gives us another relationship that's going to be very handy indeed. Now I'm going to introduce a couple scenarios where the golden ratio sort of pops up without really expecting it. And the first scenario is with continued or nested radicals, which you may or may not have encountered in pre-calculus, but we're going to discuss these in a little bit detail a little bit later, right? For example, the square root of 1 plus 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 square root, and just continue forever, right? So what is this value is the question. I mean, clearly it's going to be positive because it's the output of a radical, but what is its actual value? So if I define this entire thing to be x, if this does continue forever, then this pretty much in here is the same exact thing, right? So we can see that x is going to be equal to the square root of 1 plus x. So if I square both sides of this equation, so I'm going to have x squared is equal to 1 plus x, which gives me my quadratic equation x squared minus x minus 1 is equal to 0. I have two solutions, phi and the golden ratio and the opposite of the silver ratio. This value is positive, so I'm going to choose the positive, which of course is going to be equal to phi. So that means this nested radical representation is exactly equal to phi, right? So that's an interesting thing. So the square root of 1 plus the square root of 1 plus the square root of 1 plus the square root of and so on is equal to phi. That's interesting, I think. Another scenario is what we call continued fractions, which we'll definitely get into later. And those are things such as 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 plus 1 over, and so on, right? So again, this is clearly a positive number, but I want to know what its value is, right? So take a guess at what you think this value actually is equal to. So again, this whole entire thing is x, and this piece right here is pretty much the same exact thing. So what I have here is x is equal to 1 plus 1 over x. So I'm going to multiply both sides of this equation by x, right? And clearly x can be equal to 0, so no problems there. So I have x squared is equal to x plus 1, which gives me my equation x squared minus x minus 1 is equal to 0, which looks familiar. I want the positive solution. So of course x is equal to the golden ratio, right? So I have this other beautiful and fascinating property. 1 plus 1 over 1 plus 1 over 1 plus 1 over and so on is equal to phi, right? So if I want to approximate phi, I can use this, a finite representation of this fraction. So we can say this is approximately equal to 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 plus 1 over 1. So that would be an approximation to the golden ratio, right? So that's one way to approximate irrational numbers if you have a continued fraction representation of it, right? Which is very, very useful. One should be able to see, of course, that if I just have 1 over 1 plus 1 over 1 plus 1 over 1 plus and so on, that is, I'm missing this 1 plus. This is just the same thing as saying negative 1 plus 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 plus 1 and so on, right? So of course, this thing is equal to phi. So this is equal to negative 1 plus phi, which is the same as 5 minus 1. And we know 5 minus 1 is equal to 1 over phi, right? Which, as we know, is the silver ratio. The last example of the golden ratio that I'm going to be looking at is what we refer to as the golden angle, right? So what is the golden angle? It's sort of like the golden ratio, but now we're going to consider a circle. We're going to have 2 points here, right? And we're going to have some angle with respect to the center, right? Oh, that doesn't even match, does it? Oh, there goes my circle. No. Alright, there we go. I made it gold. Alright, so this is going to be theta. This is going to be y, and this is going to be x. So clearly y is less than or equal to x, and you can probably see. So suppose x plus y over x equals x over y is equal to phi, right? Therefore, theta is equal to the golden angle, right? So what is the value of the golden angle, right? So we already have an exact value for the golden ratio. Let's see if we can derive the golden angle value, right? So we can clearly use the circumference of the formula, circumference of a circle formula, which is 2 pi r. Or theta is just a fraction of 360 degrees, right? So the fraction, since theta corresponds to the arc of y, is just y divided by the total x plus y of 2 pi, right? So what I can do is I can divide top and bottom of this expression by y, and that's going to give me 1 divided by x over y plus 1 times 2 pi. So I already know that x over y is equal to phi in order to choose or to form a golden ratio to make a golden angle. So that's just going to be 1 divided by phi plus 1 times 2 pi. So phi plus 1 is equal to phi squared. We already proved that, right? And phi squared is the same thing as 1 minus 1 over phi. No big deal there. So we know 1 over phi is the same thing as phi minus 1, right? So this is just the same thing as saying 2 minus phi times 2 pi, right? So that's just the same thing as saying 2 minus 1 plus the square root of 5 divided by 2 times 2 pi. And then I can distribute this 2 inside to cancel out that denominator. And I have this is equal to 3 minus the square root of 5 times pi. So that is my golden angle. And I guess I'll give it a cute name. G star, right? The golden angle. G theta star, right? And so this is, of course, in radians. You can find the approximation to be about 137.51 degrees, right? So that's the golden angle. So that's the perfect angle that makes everything beautiful if you want to do like architecture, design, or whatever. Um, but anyway, that's just some special properties and some special applications and a couple scenarios for which the golden ratio sort of pops up very magically and unexpectedly as well. Definitely there are a lot more scenarios for which the golden ratio is important. We're going to bring those up when we actually need to. One of the special cases, of course, in the set of Fibonacci numbers, which we're going to discuss very soon. Hope you enjoyed.